All right. Hello, everybody. Sorry, this is a little late getting posted. This is, let's see, 1, 2, 3, 4, 5, 6, 7, take 8 of this video. I would post the outtake bloopers, but they all involve a lot of profanity, so I'm not going to do that. Today, what we're going to do is talk about variations on standard Turing machines. So last time what we did is we kind of recapped our colloquial explanation or description of a Turing machine, and then moved on to a more mathematically rigorous definition of what a Turing machine is, how it can do what it actually does, and then used that mathematical definition to motivate all the way through to a really, really famous, very important result called Turing's thesis. And so if you haven't watched the previous video, I definitely would at least skip to that part because Turing's thesis is one of the central cruxes of the entire class. Effectively, what Turing's thesis says is anything that a general purpose digital computer, like the one that you're watching this video on, can do, can also be done by one of these theoretical Turing machines that we've been talking about. So while it may seem really far-fetched to think about trying to stream video, for example, over a Turing machine, it is possible to sort of get down in the weeds and look at a byte-by-byte, bit-by-bit representation of a video and go through and actually generate a transition function that allows you to process and sort of relay that video. So Turing's thesis is really important ultimately because it allows us this definition of an algorithm that says that an algorithm is effectively equivalent to a Turing machine in that if you give me a problem on the tape of a Turing machine, and I can construct the inner workings of a Turing machine. So I can create a finite state machine for its control unit, and I can put together a transition function that takes that problem input and constructs a viable output that is an element of the range of the function that's representative of your problem. Then I have created an algorithm. And so what this definition is doing is it's taking our sort of common understanding of what an algorithm is, and it is taking it all the way down to this sort of theoretical basis of these rules that we're effectively playing to make a Turing machine that actually performs some task. And so that allows us to look at algorithms from a theoretical perspective, not necessarily the higher level perspective that you see in something like the advanced algorithms class or something like that. So ultimately, at the end of that path, we are going to get to a much more rigorous kind of mathematical definition of what computability actually means. So what does it mean for a problem to be computable? What are the practical or the pragmatic considerations around the computability of a problem, et cetera, et cetera. But before we get to that point, what we want to do is take a little bit of time and talk about variations on this idea that we introduced last time of a standard Turing machine. And so last time we talked a little bit about how the definition in the textbook of a standard Turing machine is slightly different from the definition that I gave in the lecture slides. And in fact, the standard definition in this text and the standard definition in the text we usually use for the grad course are also slightly different from one another. And so in those sort of three colloquial examples, we identified that you can make slight alterations to the rules or to the definition of the Turing machine and actually arrive at a machine that can do exactly the same thing as the other slightly altered definitions. So all of this conversation about standard Turing machines and all the equivalencies thereof is really predicated on the idea of an equivalence class. And so if you think all the way back to the very beginning of the semester, I think lecture 2 of week 1, we talked about equivalence classes as this kind of mathematical construct that was a prerequisite for understanding some of the content in the class. And so we built on that in the DFA lectures by showing that regular languages that are computed or generated by modular arithmetic could also make use of equivalence classes in order to find the kind of simplest DFA to accept the language without going through a sort of brute force exhaustive way of generating the finite state machine. So here, what we're going to do is use the exact same idea, but we're going to kind of generalize it up to things that we've been doing in the class that we haven't necessarily been calling equivalence classes. And so if you think of all of the different sort of theoretical constructs that we've been talking about, we have things like DFAs and NFAs and regular expressions and regular grammars. And we spent a fairly long amount of time, or a very large amount of time, talking about Theorem 4.1 that allows us to kind of put all of those things together, right, to equate a lot of these things. It wasn't Theorem 4.1, it was a couple of different theorems in chapter 3. So what we did is we effectively showed that DFAs and NFAs and regular expressions and regular grammars can all kind of compute the same things, right? They can all accept the same kind of languages. And what we did is we grouped those languages into language families. And that first language family we called the regular expressions. Then we kind of extrapolated out to context-free languages and showed that the various different ways, push-down automata, context-free grammars, the various ways to accept those languages were also equivalent. And so what we're going to do now is we're going to take that out maybe another level of abstraction. And we're going to start talking about two different Turing machines being equivalent if they can effectively solve the same types of problems. And so we're going to colloquially kind of call that, in big air quotes, computational power. And we're going to kind of kick the can or punt on actually defining what computability is until a little bit later, probably next week sometime. So the focus of the conversation we're going to have today is really around all of the different types of bells and whistles and things that you can add to the standard Turing machine definition, either the textbooks or mine. And you can use those bells and whistles to actually build algorithms for specific problems, specific purposes, and you can do so more easily with one standard definition than another. But all of these standard definitions of a Turing machine actually have the same computational power. So by adding these additional bells and whistles, you're not actually allowing a new machine to do more computations or solve more problems than the original standard Turing machine. What you're effectively doing is arriving at some definition that allows you to more easily communicate your algorithm. So while a standard Turing machine, as we have explained it in the lecture videos, or the textbook gives to you, you could derive whatever algorithm you want on that machine. There could exist some other standard Turing machine definition that allows you to express that algorithm much more succinctly or much more easily in terms of actually trying to derive the algorithm itself. So the very first example of this is going to be what's called the Turing machine with a stay option. And so if you think about Turing machines from last week, we said that the Turing machine itself, at the end of a configuration update, it has updated some of the input symbols on the tape, and it has maybe updated its internal state inside of the control unit. And at that point, it can either move left or right on the input tape, but it cannot stay in the same place. This new Turing machine actually has that option. And so if you think about that in a sort of mathematically rigorous way, what we're saying is in the transition function for a Turing machine with a stay option, we're going from the internal state of the control unit and some input symbols on the read-write tape to some potentially new state in the control unit, some potentially different set of symbols on the tape, and we're either going to move to the left, to the right, or stay in the same place for the read-write head. So it might seem like by adding this new option of behavior for the read-write head that we have somehow expanded the number of problems that our Turing machine can actually solve. So because we have a new feature, potentially we have problems that can be solved using that feature that would not be solvable by a Turing machine without that feature. And so the fundamental question we want to ask ourselves kind of over and over and over in this lecture is, have we actually modified this machine's ability to perform computation? Have we added problems that can be solved by this Turing machine that were not solvable by the previous definition of what a standard Turing machine is? And so here, basically all I'm asking is adding this option allowing me to do something special that the previous standard Turing machine definition could not actually do? And it turns out, no, that is not the case. So even though we've added a new feature, that new feature does not actually provide any sort of computational power. It may allow us to more succinctly communicate an algorithm, but it does not allow us to solve problems that were previously unsolvable with our original definition of a standard Turing machine. So if that's the case, the very first question that you might want to ask yourself is, why is that the case, right? So why are these two things equivalent and they have the same computational power, even though we just added a new feature to the machine? So if you think about what a Turing machine's instantaneous state consists of, last time we talked about the turnstile notation, and effectively that turnstile notation gives you three different pieces of information. It gives you the state in which the current, or the state in which the control unit currently sits. It gives you the input tape symbol that's currently being read, so it's the position of the read-write head. And it gives you the state of the input tape at this like sort of current time step. So what we can do is we can effectively leave the control unit state untouched. So in the transition function, we can effectively just have the exact same state as the output of the transition function. And we can do the exact same thing with the symbol that's currently being processed by the read-write head. So if we are reading an A, we could simply just replace that A with another A, and we haven't made any updates to the current state of the input tape. So if you think about the sort of turnstile notation of what that update would be, at this point we have changed literally nothing. However, we would be forced to make a move either left or right. So in order to essentially simulate this new feature of the machine, all we need to do is move to the left and then immediately back to the right, or to the right and then immediately back to the left. So because we can effectively just interject some additional transition rules, we know that we can simulate anything that a machine with a stop state can do using our original definition that did not allow the read-write head to stop. We effectively do that by just moving to the right and then immediately moving to the left, or moving to the left and then immediately moving to the right, while retaining the control unit state and the input tape state. So the idea that we kind of just fleshed out is often referred to as simulation. And so simulation is a really, really important technique when you're trying to express the equivalence of two different Turing machines. So it is not true that you can just make any change to the definition of a Turing machine and arrive at a computational construct that has the exact same computational power. In order to prove that one machine has the same computational power as another, what you have to be able to do is simulate one machine with the other. And so effectively what this is doing from a sort of formal perspective is we're taking some Turing machine, and we can call it M, and we are writing onto the read-write tape of machine M some initial configuration of a new Turing machine that we can call M prime. And so what we're doing is we're writing the definition of that Turing machine that we want to simulate onto another Turing machine that we refer to as the simulator. And so then what we can do is we can take the transition function rules of our simulator and then use those transition function rules to update the configuration of the simulated Turing machine using the transition function rules that are also located on the tape of our simulator. And so if you think about a class project that you might have done in something like Computer Organization 1 or Computer Organization 2, effectively in that class what you're doing is you're simulating a CPU or a processor using a higher level language, typically something like C++ or Java. And so in that case, what you're doing is you're simulating very low-level behavior using a fairly high-level programming language. And we're doing exactly the same thing with this Turing machine simulation. You're using one Turing machine to simulate the behavior of the other by writing the definition of the machine you want to simulate onto the memory of the Turing machine you're using to do the simulation. So strictly speaking, in order to show the equivalence between two machines, you have to be able to show that one machine can simulate the other and vice versa. So M prime can simulate M, but also M can simulate M prime. In a lot of cases, fortunately, this is fairly trivial. And so if you think about our previous example, in order to simulate a standard Turing machine using our definition from last week, with a Turing machine with a stop option, all you have to do is ignore the stop option or the stay option. So if your transition function never makes use of the S rule or the S transition denoted here, we know that that definition would effectively just be exactly the same as the definition that we had last week. And so trying to simulate a standard Turing machine with a stay option Turing machine is fairly trivial. However, the other direction required us to kind of outline this algorithm that allows us to make the simulation. So one thing I want to note here is that actually performing all of the detailed sort of arrangement of a simulation is certainly something that is useful to do. It is not necessarily a thing that I'm super interested in hammering home in this course. In the graduate version of the course, I'm sure that that is a thing that is much more high priority. But for now, what we really want to focus on is these kind of higher level algorithmic ideas. Just going forward, thinking about homework and things like that, really the test here is going to be making sure that everybody can understand how to simulate one machine on another, effectively using whatever rules are outlined for the simulator Turing machine. And we're going to go through several examples that kind of make that more obvious. So one of the most important and sort of most prevalent things that you can do to extend the definition of a standard Turing machine that helps you write these algorithms that show the equivalence of different types of Turing machines is to segment the tape into what are called tracks. And so if you see this diagram here, if you take the outside rectangle, that outside rectangle is just the tape. That's exactly the same as we've been seeing it all along. But now, instead of having one set of characters on the tape, now we are allowing 3 different sets of characters in every position on the tape. And so if I have the read-write head at the first cell, I would not only be reading an A, a 0, and a capital A from the Cyrillic alphabet, I would also, or instead of just reading an A, I would be reading all 3 of these. So an A, a 0, and a capital A from the Cyrillic alphabet. So when I moved the read-write head, I would go to subsequent columns instead of subsequent cells. And in this way, I can actually keep track of multiple things using only a single tape. And so the 2 things to note about tape tracks are that, as we showed in this example, you can have an entirely different alphabet for each of these tracks. And so up here, we might have just the lowercase alphabet. Here, we might just have 0s and 1s. And here, we have the Cyrillic alphabet. We could just as easily have whatever alphabet we want. And we could also have many more than 3 tracks. So we could have 4 or 5 or 19 tracks. And in one of the examples we're going to go through near the end of the lecture, we're actually going to use 4 of these things, or effectively orders of 2 of these tracks. The second thing you want to note is that really the idea of tape tracks itself is an extension of the standard definition of a Turing machine. And so we can think about why we can make that change the definition without changing the computational power of the machine. At first it might seem really strange, but there's actually a really easy way of doing so. Basically, what we can do is instead of saying we have 3 entirely different alphabets, we could effectively have one alphabet that has ordered triplets of different alphabets or alphabet symbols. So in that one alphabet, we would have effectively all of the possible combinations of each of these alphabets compressed into some triple. And then that triple would be represented on the single tape. So we know that anything that happens in a 3-track tape can be done as 1 track on a single tape because we can make that compression. And that same argument happens for 4 tracks or 5 tracks or 6 tracks or 7 tracks. And all of those arguments are kind of the same. We could have 7 tuples or 8 tuples or whatever with a single vocabulary, which compresses all of these tracks back into a single track on a single tape. And that's why having multiple tracks doesn't actually improve the power of the machine. We're basically just extending the alphabets that we can have on the same tape. So the next thing that we're going to talk about is a Turing machine with a semi-infinite tape. This is an example because the textbook does not use my standard definition of a Turing machine. And in fact, we actually covered why these things, these types of Turing machines are the same as a completely infinite tape Turing machine in the last video, but we kind of did it colloquially. And so the standard definition that I use in the lectures is called a semi-infinite tape, and the reason is I put a rigid boundary on the left end of the tape. So if you go back to the slide deck, I think it was 20 and 21, what you'll see is that in all of those diagrams, the right-hand boundary is erased. So you can go however far you want to the right end of the tape, but at the left there is a rigid boundary and you can't actually go before that boundary to the left. So the textbook uses a tape that does not have that rigid boundary. But last time we kind of explained how it doesn't actually really matter because both of those types of Turing machines have the same computational power. And so what we're going to do now is kind of show that via a simulation. So we can simulate a semi-infinite tape by taking all the transition function rules for a completely infinite tape and then restricting the number of times the transition function allows a left movement. So effectively what we're doing here is we are not allowing the infinite tape to reach the left-hand boundary of the semi-infinite tape. We can simulate the other direction by effectively taking the input as it is on the original tape of the machine, of the semi-infinite tape of the machine, picking it up and then moving it to the right and the number of moves equivalent to the maximum number of left moves that we see in the transition function. And because we do that, we never actually hit the left-hand boundary. We're incapable of using that left-hand boundary in the actual algorithm. And so even if there's only one cell between the left-hand side of the input and the left-hand boundary, the algorithm is completely unaware that the left-hand boundary is there. And so we can't distinguish the difference between a completely infinite to the left tape or a tape that has a boundary that is inaccessible to the left. The text uses a different simulation that might be more straightforward for some people to think about, and so I'll bring it up here. Basically what they do is they use a 2-track tape to simulate a semi-infinite tape. Or a 2-track tape that is semi-infinite to simulate a completely infinite tape. So if you think about the tape having some middle point, track 1 would effectively provide all of the input to the right of that middle point, and then track 2 would provide all of the input to the left of that middle point. And because both of these things are semi-infinite, they allow you to go an infinite number of spaces in either of those directions by using the corresponding track number. So either of those simulations will provide the same result. So the next type of modification that we can make is called an offline Turing machine. And so from the very beginning of our discussion about Turing machines, we denoted that we do not need the idea of an input file. And so if you remember, push-down automata had not only a stack that they had to manage, but you also had an input file that worked exactly the same way as the input for a DFA or an NFA. It's effectively a read-only piece of input that you read from the left to the right, character by character, and it cannot be updated like the read-write tape of a Turing machine, where the input for a Turing machine is located. So if you want to recall, everything prior to Turing machines had an input file, and that input file drove everything we talked about for that construct. And so if you try to go back to a DFA and remove the idea of an input file, basically nothing that we talked about in the entire semester would actually make sense, because all of our algorithms, all of our everything assumed that you had an input file, and the input file was read in a hyper-specific way. So the natural question becomes, what happens if I add an input file to a Turing machine? It kind of makes sense that if I had such an input file and I was able to put restrictions on that input file, I would be able to achieve more power or solve more problems than a standard Turing machine that does not have an input file. And it turns out that this is not true. A Turing machine can have an input file or it cannot have an input file, and it doesn't actually matter. The presence of an input file does not allow a Turing machine to solve more problems than otherwise. So if we think about what we're trying to discuss, visually, this is what a read-only or an offline Turing machine looks like. We have this read-only tape at the top. This thing would be populated with the input for a problem. So for example, if you were trying to build an acceptor, this would be the string that you're trying to determine if it's in the language or not. That would be fed into the control unit, which would then use the read-write head in order to produce some sort of output. So if we wanted to simulate a standard machine with an offline machine, all we need to do is take the input file and copy the input file to the tape character by character. So we start from the left and we read the first character, then copy it to the tape, reread the second character, copy it to the tape, the third character, so on and so forth. Then after we had all of the input copied to the tape, we would proceed with whatever algorithm was implemented by the Turing machine. So we would proceed with that algorithm as usual, and all that's left is to profit. We've effectively done exactly the same as a standard Turing machine, except we had this nice little offline input file that we didn't necessarily have to have on the input tape at time 0. Now, if we want to go in the other direction, so now what we want to do is we want to simulate an offline machine with a standard machine. What we can do is we can use a 4-track standard Turing machine in order to do this. And so recall, we showed that a 4-track tape can do exactly the same stuff as a 1-track tape. So showing that we can simulate this machine with a 4-track tape also shows that we could simulate this with a 1-track tape. It would just be slightly more cumbersome to do so. So basically what we will do is we will take the input provided in the input file, and that will be simulated by the first track on the tape. And so in our standard Turing machine, we will locate all of the content that would be in the read-only input file for our offline machine, and we'll put all of that data, or all of that information, into the first track. The second track is going to be used to keep up with the position that we are reading through the input. And so the second track is effectively a pointer that we've been using this entire semester kind of implicitly. What this does is it tells you if you are currently processing the first or the second or the third or the fourth character inside of the input. And each time you process one of those letters or one of those symbols, it goes to the next position on the track. The third track is going to represent the tape of the offline machine. And so if you go all the way back here, we see the offline machine still has this number 3 component here called read-write tape. That read-write tape is exactly the same read-write tape as a standard Turing machine. And what we're doing with this third track is actually just representing that tape. So anything that would go onto the tape of the offline machine goes onto the third track of the only tape in the standard Turing machine. Then the fourth track is going to show the position of the head on that offline machine's tape. And so effectively what we have is we have a track that takes care of all of the state in the input file. We have a track that keeps track of where we are in the input file. We have another track that keeps track of all of the state in the offline machine's tape. And then we also have a track that keeps track of where the read-write head is on that read-write tape. And so basically any move of this machine, so any move of the tape in the machine, will do a couple different things. It will advance tracks 1 and 2 to identify which letter or which symbol is currently being processed. As that machine is being processed, it will be passed into the transition function of the Turing machine, and then that transition function will update tracks 3 and 4 by updating track 3 with the character replacement that would happen on the offline machine's tape, and then updating track 4 to denote whether the read-write head is moved to the left or to the right. And then we could do whatever transition function we wanted to do from the offline machine. The shape or the size or the whatever of that transition function doesn't actually matter. We can simulate however many rules we want on tracks 3 and 4, and so we know anything that we could do in an offline machine we could also do with a standard machine, as long as we kind of split it up into these different tracks, or if we used a more advanced alphabet in order to keep track of all these individual things as part of a single element in the alphabet. So those are what are called I believe they're called the trivial. So I'm checking now. They are called the minor variations of a Turing machine. All of that stuff is covered in section 10.1 of the textbook. And the explanations in the textbook are, in my mind, a little bit verbose. And so I hope that this video is helpful. I'm trying to kind of give a colloquial understanding, or maybe a little bit higher level understanding of what's actually happening. And then you can use the textbook to kind of fill in the details if you're interested in those details. So the next part, or sort of the second half of this lecture, really deals with section 10.2, which is centered around Turing machines that have more complex storage capabilities. And so the motivating idea here is that if you were looking at one of these Turing machines as we have explained them so far, or as we looked at them last week, the storage capabilities of those Turing machines is pretty rudimentary. You effectively have an array, be it semi-bounded or completely bounded or not bounded, or not completely bounded, but semi or infinite array. And you have to ask yourself, if I was able to represent the internal storage of my machine with something more verbose, with something more complicated, would I arrive at a Turing machine that is actually capable of solving problems that are not solvable as long as I'm using this kind of rudimentary concept of internal storage? It turns out that it does not matter how complex your Turing machine internal storage becomes. Typically, this is not a true statement. It is not possible to get to a Turing machine that is capable of solving additional problems by simply modifying the storage capabilities of that machine. And so the text gives two examples, and I want to quickly go through those examples. And for section 10.2, what I was saying about section 10.1 is maybe even more true. So the text goes through a tremendous amount of detail, and I think that if you were just trying to read the textbook, potentially you could miss the forest for the trees. And so what I'm going to try to do is give you the overview of the arguments that are used in the text, and then if you're interested in the details, you're welcome to go and inspect the trees however you want, but I don't necessarily want the entire class to sort of get trapped or get stuck on those explanations. So the first one is called a multi-tape Turing machine. And so this should not be confused with a Turing machine with multiple tracks. What this is actually saying is I have a single control unit that has multiple read-write tapes, and those multiple read-write tapes have independent read-write heads. So here, it just so happens, serendipitously, that both of these read-write tapes have the read-write head in the same position. This isn't required. This one, the top tape could be reading position 1, the bottom tape could be reading position 7. There could be 98 additional tapes with whatever read-write head configuration you want on them. These are called multi-tape Turing machines because we aren't splitting a single tape into multiple tracks. We're actually providing multiple internal storage mechanisms, or we're providing multiple input tapes with independent read-write heads in an attempt to maybe broaden the types of problems that we can solve using this type of Turing machine. So like we were saying before, if we simulate in one direction, a lot of the times this is really, really trivial. And in this case, we can simulate a one-track standard one-tape Turing machine by just not using the additional tapes. So if we have a 5-tape Turing machine and we remove 4 of those tapes, we can do everything that we would originally want to do on that single tape. There are some details around how you need to do that. Effectively, you would need some sort of delimiter to collapse the tapes into a single tape. But after you work around the details of what that delimiter looks like, you know that you can effectively store a countably infinite amount of information on a Turing machine. And the combination of these 3 or 4 or 5 or 19 countably infinite sequences of input can be compressed into a single countably infinite tape. We would just need some way of denoting where one tape starts and one tape stops. And you could manage storage by doing exactly the same types of algorithms that you do with array allocation in C. You would effectively increase the size of one of the tapes by shifting all the other tapes in one direction and then freeing up a cell for the tape that you're trying to expand. So there are some technical details around how to do the simulation, but conceptually it kind of makes sense. If you want to simulate a one-tape machine, you can do that by compressing whatever number of tapes you have into a single tape, and then sort of ignoring the other ones. So in order to go the other direction, so what we're going to try to do here is instead of simulating a one-track or a one-tape machine, we're going to try to simulate a multiple tape machine using a one-tape machine. We're going to use the same idea that we used for the offline Turing machine. And so basically what we're going to do is we're going to recognize the fact that our offline Turing machine's input file is effectively just a watered down version of a tape. It is a tape that you can only read from, and so it's a tape with some limited functionality. So what we're going to do is we're going to split the 2 tapes for our multi-tape machine into a single tape with 4 tracks. And so the first track at the top is going to simulate the state of the first tape. And so each of the characters on the first state, or each of the symbols, is going to be represented on this first track. Then the second track is going to keep track of the position of the read-write head. And so if the read-write head is in this third position, or this 2 position, if you're using 0-based counting, this would be a 1, everything else would be a 0, or you would mark this with an asterisk and everything else would be a blank. However you want to do it in your alphabet, it doesn't really matter. We're just going to keep track of where the read-write head is on this track. So for every other tape, we're going to have 2 additional tracks. And those additional tracks are going to keep track of the exact same 2 pieces of information. So the first one is going to take care of the actual state that is written on that tape. The second one is going to take care of the position of the read-write head. So it's going to denote which of the cells that head is actually reading. And so, as I said, it doesn't actually matter how many tapes you have. If you have 500 tapes, you could have 1,000 tracks, and each of those 1,000 tracks would either track the state of the tape or the position of the independent read-write head as it reads that independent tape. What we've shown here is for any multiple number of tapes, we can compress all of that information or all of those algorithms into a single tape with multiple tracks, because we know a single tape with multiple tracks can then be compressed into a single track on a single tape using fancy alphabet. We know that our original Turing machine and this new fancy multi-tape Turing machine can actually do the exact same simulations or the exact same computations, and one can't do more stuff than the other, which is the main point. The slightly more complicated case is if you want a multi-dimensional tape. And so for sort of argument's sake, this is a grid. It isn't actually a tape in our traditional sense, because here we can move the read-write head either up and down or left and right. And so this is, in a lot of ways, very different from, for example, a multi-track single tape machine, in that there is only a single read-write head. And that read-write head can move to any of these cells independently. So it can move up and down, or it can move left and right. It is not confined to reading only a single column at a time. What we want to do first is we want to try to simulate a standard machine using this multi-dimensional kind of fancy machine. And it turns out that this is the easy way, or the easier case. So in that case, all we need to do is take all of the dimensions, or all the rows below the top row, and effectively throw them away. What we want to do is compress all of that information into the top row using the same argument that we used before. We can use a delimiter to indicate when we moved from the original row 2 to the original row 3, so on and so forth, and store all of that same information in that very first row. So this special delimiter, the special character, is going to tell us when we would otherwise move to a second row, and in that way we can use our original algorithm and just search for the delimiter instead of using a transition function to move up and down. We would effectively just seek to either the third of those delimiters, the fourth of the delimiters, the fifth of the delimiters, to get to the third or the fourth or the fifth row, respectively. So then, after you have made that compression, all you need to do is make sure that anytime in your algorithm you would make the read-write head go up or down, you would actually make it seek to the right or to the left for the delimiter character that indicates that you're going either up or down through the rows. And so counting those delimiters would be the new way to go up and down through the different rows. And then you're done. So we basically use the exact same trick that we've used 3 or 4 different times in this lecture so far. We take multiple rows of information, we compress them into a single row, and we use a delimiter to determine when we otherwise would have gone to a different row. And in this case, the exact same argument applies for reallocating space. If you run out of space for a delimited row and you need to add more, you effectively pick everything up to the left or to the right and shift it to free up space on that row that you're trying to allocate space for. You'd use the exact same kind of algorithms that you would use in something like C to extend an array. So simulating a multi-dimensional machine with a standard machine is significantly more complicated. And this is the kind of thing that I would expect people to be able to logic their way through at the end of the class. I'm not super interested in everybody being able to go through all of the technical details in each individual transition function rule for all of these algorithms, or deriving your own transition function for algorithms for problems or Turing machines that you've never seen before. What you should be able to do is come up with an algorithm that kind of looks like this one. So the first thing that we need is an address scheme that tells us the position that our multidimensional read-write head will be in. And this thing doesn't necessarily have to be fancy, right? You can pattern it after effectively a Cartesian grid. So you can let the left boundary of our grid be 0. You can let the top boundary of the grid be 0 for up and down direction. And then any move to the right would be a positive integer in our Cartesian coordinate system. And then any move down would be a negative value for the up-down direction. And so to kind of make that clear, we would consider this to be the 0th row. Any time the read-write head is positioned at a row less than this, it would go down by 1. And so this would be the -1 row, this would be the -2 row, the -3 row, etc., etc. Likewise, for the right direction, this would be the 0th column, the 1st, the 2nd, the 3rd, the 4th, the 5th column, so on and so forth. And remember that we've already shown that a tape that is infinite in both directions is equivalent to a tape that is the same, infinite in only one direction. So we don't necessarily have to deal with going left negative or up positive in the positive numbers. We could do that if we wanted to, but we're making the argument that we don't have to for simplicity's sake. So after we have determined this Cartesian coordinate system, or I guess a coordinate system derived from the Cartesian coordinate system, all we need is a 2-track system that takes inventory of exactly the same 2 pieces of information that we have taken inventory of for the entire lecture. One, we need to hold the actual contents of the multidimensional grid, and on track 2, we need delimiters that tell us where on the multidimensional grid that piece of information would be. So to make that concrete, we could go back here and we could say, if we are talking about this information right here, their track 1 would have whatever value is here. So if it's an A, if it's a B, if it's a 1 or a 0, whatever, this would be in track 1. On track 2, we would have something that looks like some delimiter, maybe a left parentheses, for example, and we would have the value 0, 1, 2, 3. So we would have a 3 as that coordinate. We would have a different delimiter, possibly a comma, followed by the up-down position, and in this case, -1. And then that would be followed by a right-hand parentheses, for example, that tells us that that is the coordinate for the very first position on track 1. So while track 2 has many, many, many more cells that are dedicated to a single piece of state, we can use those delimiters to keep track of which thing on track 1 corresponds to which element on track 2. And using that idea, we can effectively compress this entire 2-dimensional array into a single array that has multiple values in each cell effectively. And so note that you could make the exact same argument for a 3-dimensional grid or a hypercube or a 19-dimensional grid or whatever you wanted to do. And effectively all that would change is the second track. So in track 2, instead of having just some ordered pair, you could have an n tuple that determines exactly what quote cell in the multi-dimensional grid you're pointed to for the value that is stored on track 1. Okay. So that draws us to the end of section 10.2. There are 2 additional really huge things that we have to talk about to finalize chapter 10 this week. One of those is the non-deterministic Turing machine. It turns out that this is not a super huge deal, and it has a lot of the same ideas and concepts in it as we talked about with non-deterministic versus deterministic pushdown automata. And we'll go through that at the beginning of next lecture. The last thing we have to talk about is actually a super huge deal, and that is a universal Turing machine. So the idea of a universal Turing machine is that we can use this concept of simulation to actually build a Turing machine that is capable of solving multiple problems at once. And so right now, what we've done is kind of equivocated algorithms and Turing machines, but we all know that the digital computers that we use every day, you don't have to throw out your digital computer and get a new one every time you want to do a different project. So if you don't have one machine that's dedicated to Microsoft Word and one machine that's dedicated to PowerPoint, et cetera, et cetera. And so universal Turing machines are the theoretical step that allow us to make that leap, to create a Turing machine that can actually write a modifiable state of a Turing machine on it, so that we can modify the internal workings of the Turing machine that we're simulating to implement an algorithm that fits an arbitrary problem. So as long as we give the universal Turing machine a problem that is computable, we can modify the tape to simulate a Turing machine that can actually compute that problem that we're trying to solve. And so theoretically, that is what we've done with general purpose processors. So with that, I will let you get back to whatever you were doing before, but I really appreciate everybody tuning into these videos. I've watched as the numbers of views kind of climb, and it's kind of heartening to me that people are actually taking it seriously. If you are interested, the first quiz should be posted over this coming weekend, and effectively that quiz will cover a lot of the theoretical concepts in these last several lectures. It will not necessarily be super math heavy. What it will focus on is your ability to sort of answer theoretical questions about what Turing machines are, how they work, why they're important, and the sort of things that we can actually do with them. So look out for a new video on Wednesday or sometime Thursday containing the non-deterministic Turing machine and universal Turing machine discussions. And until then, please send me an email if you have any questions, comments, concerns about anything, and I will respond to those as soon as physically possible. Thanks, everybody.